It's okay to pretend to be short.
Hi, everybody. So thank you for coming at the Rubin Galaxy collaboration section. We have 3 sections on galaxies, and this is the one who is more dedicated to the science collaboration. So I will start with an introduction of the science collaboration for those of you who don't know us and would like to join. Then I will speak in general on how LSST will be very important for galaxy formation and evolution. And then we will go into topics that are more related to what we are doing right now. One is a photometric redshift and SED fitting challenge. We will have a low super brightness science presentation and DP2 readiness. And then we will see new results from DP1 and DP2. So let's start with this more general part. Just a reminder, code of conduct, harassment of professional conduct is not permitted. If you experience or witness it, please reach out. And you can come to me and I will speak with the organizers. And the Rubin Observatory adheres to the principle of kindness, trust, respect, diversity, inclusiveness in order to provide a learning environment that produces rigor and excellence. For our collaboration, you find the web page here, and you can see more about our structure. And the co-chairs are myself and Sugata Kavirai. I'm usually here at this RCW, and you will meet Sugata LSST Europe 8. We are around 450 members. The collaboration doubled in the past 2 years. And our goal is to understand galaxy formation and evolution. So what is special about LSST is that we will have very large statistics from the very massive galaxies to the very faint galaxies. We will find low super brightness features around galaxies like tidal tails, merger remnants, etc. And we will study the connection between the galaxy properties and the dark matter halos. Another important aspect is the galaxy cluster intercluster medium. As you know, with the LST, we will have a very good low super brightness feature detection, and intercluster medium is also one of these detections. The roadmap is in these 2 papers, so you can read it. It's Robertson 2017 and Robertson 2019. We are organizing working groups. So this is the list of the working groups. So we have AGN, galaxy environment, morphology, low super brightness, SED fitting and photometric techniques, strong lensing, and survey strategy. We also have a lot of liaison with other groups with the project. So that for in-kind operation manager, contribution to the evaluation committee representative, survey cadence optimization committee liaison is Louise that I just saw is there. So if you want to speak with her, because this is one of the most important topics we will have to address this month. The Rubin Euclid the working group, data management liaison, commissioning, and DEI. This is our web page. So if you want to join or find information about the collaboration, you can just click on it. You see on the left, you have the working groups, the members, the governance documents, technical reports, publication, active projects, and you can apply for membership if you want to join us. These are the working groups. So this is the apply for membership page. Something important, we don't require data rights. So everybody can join the collaboration, but only people with data rights can work with LSST data. But you can join if you are an expert in galaxy formation and evolution. What are our current activities? So most of the work we are doing is manage the in-kind contributions on the science collaboration, and you see the major topic of the collaboration. So LBS, photo Z and SED fitting, the measure of the morphological parameter, and distance measurements. And then there are some tools that can permit us to cross-match LSST with external data, so that people from radios or millimeter, etc. We have regular activities. We meet once a month by telecons, apart the months where we have meetings. Like in June, we had our collaboration meeting. Now we're having the RCW. Then there is summer vacation and so we will start again with the telecons in October. face-to-face meeting. So we met in Paris this year, and that was very good meeting in which we could really start to prepare for DP2 and DR1. I will show you some highlights of the meetings. And we have challenges. So, for example, the Law for Brightness Working Group challenge, and as I will say, there will be a photometric redshift and a CD fitting challenge and a morphological parameter challenge in the next months. We prepared for the DP2, and now we are preparing for DR1. For DR1, the main question is that what do we want from DR1? How do we visualize DR1 in this collaboration? We have to send our feedback to the other science collaboration, to the SAC, to the SCOC. If you were there this morning, you see how much complex is the interplay of all the parameters that enter in the cadence and how to plan this survey. And there is this very important question. Do we want a DR1 that is defined by a year, 365 days, or do we want a DR1 that is defined by science requirements? So all these are very important questions. I posted in the Slack channel the request for help, and please reach out to me and Sugata if you have requirements, if you have ideas and opinions about that, because we have to give our feedback to the SCOC. This is the first look image with LSST CAM, the Virgo cluster, so it's 24 square degrees. It will be part of the DP2. So there are already people who are working on that, and we will see a lot of results and papers coming out in the next months. We discussed at the LSST Galaxy Science collaboration meeting in June in Paris, and we will soon have a wiki that will be potentially set up in CRA in India, and Yogesh Vadadekar is taking care of the setting up of the webpage and giving us access soon. And we will set up a shared database for skills and collaborations and projects and papers. And we realized that our publication policy, the one that you will find on the webpage, was too heavy for our collaboration. We don't have all these committees and people that can check all the papers and make all these steps to arrive to the publication. So we will have a lighter publication policy that we are drafting with Sugata in the summer, September, and we will propose it to you. If you know the different strategy in the different collaboration, the desk publication policy requires a lot of steps and committees that we don't have. The TVS is much easier, so that, you know, if there are no ethical issues or large conflicts, you can just publish whatever you want. And we're going towards that approach in the Galaxy Science collaboration, because we don't want to block your science, we just want to facilitate it, and we don't want to put too many obstacles between the time you have your work done and your results validated and the time where you publish. We are, for communication, we used emails for many years, and now we decide to use more and more Slack for rapid communication, and we will use email only for the big announcements. For the science collaboration members that are working on infrastructure projects that are not in kind contribution, we will set up a web page so that they can exchange among themselves. So just contact us if you have advice on any of these points. The working groups, we have to renew and revive 2 groups that are simulations and environment that have not been active for a long time. So we're looking for experts in these 2 fields. Please contact us if you feel like energetic and enthusiastically, an enthusiastic vocation to do that, because we will really need people who are active, especially now with DP2 and DR1, to revive these groups. And the WG leads will be recruited after the summer. Some initiative that can be useful for all the science collaboration member will be the Euclid DR1 morphology classification, hybrid ground plus space-based classification approach, and you should contact Eileen Lazar, the morphology data challenge, and the PhotoZ SED data challenge, of which Kasia will tell us today. I just go through some breakthrough galaxy science that we expect from LSST. This is especially for people who just joined us and they want to know what the Galaxies science collaboration is here for. So the first thing that you see about galaxies is their morphology. So one of the challenges that we will have in the next year is see how we go from this scenario on the right, that are the morphology of galaxy at high redshift. They are very regular, and many spiral galaxies that and very unclassified galaxies also at very high redshift, where you cannot really tell which kind of Hubble type you are dealing with, to the present scenario where you have Hubble types, early type galaxies, late type, irregular, and dwarfs. When we speak about galaxies, we go from masses that range between 10 to the 5 to 10 to the 13 solar masses. And this is a huge amount of morphology, galaxy ranges, and LSST will cover it all. So we go from the very, very faint object to the very, very massive. So that will be really a test bed to study galaxy morphology. The other thing is galaxy distribution and environment. So you know that on the cosmic web, galaxies are distributed in galaxy clusters, in groups, filaments, and in regions that are voids, so that we will study galaxy formation and evolution as a function of the environment. Galaxies form in a hierarchical way. In the lambda CDM, cold dark matter halos merge hierarchically with time, and galaxies where in these halos also merge. So galaxies merge to form from, as you see in the diagram, small galaxies here. So each point is a small galaxy who's merging. This is far away time, 13 gigayears ago. You had small galaxies that merge together, and with time, small galaxies merge with large galaxies to form the very massive galaxies that we observe at present. And this means that there are a lot of mergers that we will also have to consider in our studies. There is an interplay of galaxy components that poses a lot of challenges today. We have to understand how stars are formed and what is the baryon cycle, so that we know that at high redshift, galaxies were not forming many stars, and then they start to form more and more stars up to a peak around redshift equal 2, and then suddenly the star formation declined again. So that we want to understand how the star formation rate density evolved as a function of time, and we know that there are several physical mechanisms. So in a galaxy, you have cold gas, and when the cold gas collapses, you form the stars. But how this cold gas is accreted or is in the galaxy can happen in different ways. For example, when you have star formation, you can have supernovae. There is a stellar mass loss, supernovae winds, and because of that, the gas cools, so it starts to form stars again through turbulence for molecular clouds, cold gas collapse, and the star formation cycle starts again. In the meantime, nuclear activity is at the center of the galaxies, expels and accretes material. So when we have outflows, you can have jet winds, there is an outflow, the outflow can cool or heat the cluster. So be positive feedback for star formation and a negative effect, and then there is an inflow to the nuclear activity. Now, LSST cannot do everything to understand how all this happens, but there are some parts of the galaxy formation evolution in which LSST will be important. And so these are the main questions that the LSST will address for galaxy science. With optical observation, the LSST size, depth, and image quality, we can ask ourselves these questions. How do galaxies grow by forming stars and merging, depending on the environment and across cosmic time? So we will have very deep observations on a very large area, very high quality data, and we can definitely address this question. What are the consequences of feedback, so supernovae AGN, on galaxy evolution? Relative content of stellar and dark matter in galaxy and more massive dark matter halos like cluster impact galaxy formation in evolution. I won't cover everything that we can do with LSST, but I will just give some highlights and the role that artificial intelligence will have in our science, because we will have a very large amount of galaxies. So we cannot treat them with not much with traditional methods. We will go from the very faint objects that will be presented later to the very bright and massive structure like galaxy clusters. The first thing that we will do with deep machine learning is to study galaxy properties. So we have an in-kind contribution. We have several in-kind contributions on this subject. You see the references there. And I just took one to illustrate what people are doing. This is the what's called the name? I don't remember the name, but it's Galaxy Light Profile Convolutional Neural Network. Their group in Naples, and what they do simulations of galaxies on which they train the network, and then there is a convolutional network who give us the galaxy parameters. There are several parameters like the morphology, the size, the mass, the star formation rate. In this case, I just show one is the size R, and the effective radius, and you see that compared to the true value of the effective radius on the x-axis, the predicted value on the y-axis gives a very good estimate. When defining galaxy property, you can also measure morphology and star formation rate. And this is another group who measured the morphology star formation rate of the galaxy. And on the left, you have the star formation rate main sequence. So you see there are galaxies were star forming. Let me see the mouse. Okay, that are star forming that are on this main sequence, and then here you see the cloud of quench galaxies that stopped, that are stopping and stopped star formation. So we can study quenching and star forming as function of the stellar mass. How do we study supernova AGN feedback? We can use galaxy luminosity and mass function, because if the star formation efficiency was the same at all masses, in this case, or all luminosity, you can do the same with the luminosity function. The result, what we should see is the dashed line, the dashed red line. In reality, what we observe is the continuous black line, where you have a maximum efficiency around 10 to the 5 to 10 to the 11 solar masses, and then the star formation is less efficient for galaxies that are less and more massive. So we want to understand how. This is a work from JWST. To do this kind of work, you can understand what's the feedback also for different kind of galaxies. So here we have all galaxies from JWST for all different redshifts, from low redshift to from the low redshift to the very high redshift. And you see that the shape is not at all this red line that we expect here, but is more something similar to that. You see here, the star formation is less efficient, there is a peak, and here it goes down, and then it goes up again here in the local universe, otherwise it stays more or less flat. You can see how this difference in star formation, also how the supernovae and AGN feedback impact the star formation for different galaxy types, for example, early type and late type galaxies. And with the LSST, this kind of measurements will be done with very little uncertainty. So we will have high precision estimate of these physical parameters. We can build we can build morphology density relation and quench fraction density relation to see how galaxies transform from late type galaxies to early type galaxies, so that the fraction of ATG will be different in function of time, or how they stop the star formation. So that which fraction of what is the fraction of quench galaxy as a function of time, as a function of galaxy density. So here you have an example where you have different redshift at z between 1.3 and 1.9, larger than 1.9 and 3. And you see that with respect to the z equals 0 relation, this relation is still in place at z equals 2. At z equals 3, we have only 2 points, so you can say whatever you want. But you see that there is a tendency and a wish to have more statistics from LSST combined, for example, with Euclid, to know more about when galaxy are transformed from late type to early type and when they quench their star formation. If we go back to the local universe, we will be able to know more about mergers and other galaxy interactions, so that this is a simulation of 10-year depth LSST, and you can see all these features that are the results of all the mergers and interactions the galaxy went through, so that if we can measure and characterize tidal features, we can reconstruct the merger history of the galaxy and other galaxy interaction. And we can know how much mergers contributed to mass accretion and to star formation rate. This is all work by people in our collaboration, by the way. This is an example of tidal interaction feature found with the CNN, and they are shells. So you see the shell around the galaxy, streams, tails, plumes, and double nuclei. And the images are from the Hyper-Supreme Subaru strategic program that, as you know, is at the same depth of what we expect with LSST. So these groups are already ready to work on DP2 at year 1 to obtain these results on much larger scale. This is an example of transformer models that were used to detect dwarf galaxies. And what is interesting, what is difficult to detect dwarf galaxies is that there are a lot of artifacts. So instead of dwarf galaxies, you find something else. So this algorithm permits us to separate dwarf galaxies from image artifacts with 94% accuracy. So it was a big achievement by this group, by this galaxy collaboration. This is an example of intracluster light. So what does the intracluster light tell you? You have seen the tidal tails remnants around the galaxy. That's something about the merger history of the galaxy. So now we are on a larger scale. This is light, so stars that are not connected to galaxies, that are in the potential well of the galaxy clusters, so a much larger structure, but it tells you the same thing. Instead of telling you how the galaxy accreted its mass, it gives you an idea what is the mass assembly history of galaxy clusters and groups. So the light comes from these stars that are freed, and how are they freed? Probably in galaxy encounters. So this is also work from people from our team, from our science collaboration, and here you can see how all this stellar matter is all around the galaxies, and they can be defined in streams, plumes, loops. What is also interesting about that is that that these detections can be done with the CNN, always with machine learning, and they are designed to automatically measure the ICL in larger sample of images, is what we will have with the LSST, without any manual preprocessing required. So we will have, here is an example of from simulation of predicted ICL on the y-axis and the actual ICL fraction on the x-axis. And you see that with these machine learning methods, we can really reconstruct the ICL content in galaxy clusters. And this is great also because ICL traces dark matter, so you can have a measure of the dark matter content of the cluster. So this work is from the TNG 300 simulations, where the ICL profile traces the dark matter profile in galaxy clusters, so that observing the light, we know about the dark matter content of the galaxy cluster. One more thing is the stellar to dark matter connection. So gravitational distortion that are caused by dark matter, like in strong weak lensing, can be measured in LSST. And if we measure galaxy stellar mass by the LSST data, by this parameter quantification that we saw before, we can also trace the connection between the stellar and the dark matter and the star formation efficiency as function of the dark matter halo. So as you see here, we find something similar to what we have seen before, but shown in another way. On the left, you have the stellar mass over the ratio between stellar mass and the halo mass. as a function of stellar mass. And you see that it grows from large stellar masses up to a peak, and then it decreases. So it means that left and right of the peak, you form stars in a less efficient way. So again, this peak is always observed around 10 to the 11 to 10 to the 12 solar masses, and it changes as a function of redshift. So LSST will be able to build this kind of relations very easily when we will have all the measurements of the dark matter halos. We can measure gravitational distortion with Kesong lensing, and to observe these dark matter signatures, we are also building transformers and CNN. This is an example of the transformers and CNN network developed in science collaboration to detect strong lensing in simulation and observation from kids. And it's interesting because the transformer model reduces the number of false positives of 70%. So it's really impressive for strong lensing science. So LSST, just to conclude, will give us an unprecedented view of galaxy mass accretion depending on the environment across cosmic time, of the consequences of galaxy merger and supernova AGN feedback on galaxy evolution, and on the relative content of stellar and dark matter in galaxies, and the impact on galaxy evolution. This will be done. I think I put the whole version of the presentation. So Aaron will tell you more about the DP1 results afterwards. And now I leave the stage to Kasia. And I don't know if you have questions on this first part of the presentation, on the science collaboration, on what you would like to do, your opinion about how we should give feedback to the COC, or the strategy for DR1. Not yet. Input on the publication policy. Is this new lightweight what suits you the best? Okay, think about it. Kasia will speak, and then we'll go back to that.
Thank you very much.
You have to take this.
I hope so. Okay. Thank you.
Those are fun.
So thank you, Simona. I think that Simona gave a great overview on the Galaxy Science Collaboration Group. So what I'm going to present now is just a part of our discussion during the meeting in Paris, when we discussed the SED fitting procedure and photometric redshift for the Galaxy. As also Simona mentioned, we have a lot of in-kind program, and some of the programs are, promises to give the SED fitting and the main physical properties of a galaxy, as well as the photometric redshift. But we are working on a different strategies, different tools. So, during the meeting, together with Rebecca Bauer, we presented like some highlights from, but not only highlights, because we also had a lot of discussion how to proceed with the data and our perspective for our next steps, right? So I will present also what were the main points of our discussion, so we can separate it into three groups. So first, those are the challenges. So of course, we are very happy to have all the data to do our science with the galaxy, to understand the evolution of the galaxies and dark matter and everything else. But of course, the data, it's great because we are going to have a lot of data, but how to proceed with the data is much more complicated, right? So we have large data volumes. And those are really massive tasks for the one person to proceed with running codes. So we have to discuss inside the collaboration. We have to find some agreements how to proceed with those challenges, and how to work better as a group. Also, we discussed about the regular communication. Also, as Simona said, in our collaboration, we have the monthly meetings. But as the community is growing, we have more than 400 people. Maybe we should start some separate meetings dedicated to one specific task. So this is something we want to do in the future. And also challenges, because of course each of us from the group thinks that, okay, we know that we are not perfect, but our codes are the best ones, the task. But I think that we have to check, and we have to do both the PhotoZ and SED fitting challenges, and we are planning to do it soon, maybe not during the summer, but for sure after summer. So we are also going to give you some information about that, and maybe somebody else would also like to join. And also, so also we had some more philosophical discussion. So how realistic are the core properties we are going to give? So as you know, the main physical properties for the SED fits are like the stellar mass formation rate, but also AGN fraction and others. So we have to have some kind of agreement about that inside the Galaxy group. So we have those three main questions to solve. So how to proceed with the whole group of the 400 people? It's like a large group. So how to proceed inside the group? What do we really need to do our science? So which kind of common properties we have to even to check if we agree between each other, and what is missing for the dear one. So as I mentioned, the challenges are super important. So for sure, Rebecca is going to proceed with the PhotoZ challenge. Of course, for the PhotoZ, we are going to use a lot of machine learning techniques. So we have to agree which kind of sample we should use, how big should be the sample, how we can, which kind of data we can use for that. So this is still a lot of questions we have to find the answer for. And we know also that desk group has also PhotoZ challenge for some kind of different tasks. So we can to discuss together like how desk prepared their challenges and the data and etc. For the SED challenge, in which I'm more interested in, and probably I'm going to lead it. Let's see. So I don't know if you're aware of the work from 2023 of Pacifici et al. When we also did this kind of SED challenge, but for much smaller sample. We had just two samples of Galaxies, one on the local redshift and on the redshift 3, and we used all the different codes which are now on the market to check where we agree and we do not agree, and what are the uncertainties for different codes. So this is something we are going to proceed with. And also we have to do some documentation. We want to work on that and to give to the whole community the documentation how we are dealing with different codes and how other people can also use it, because we want to be very open with that. So the basic requirements for us, it's the redshift, of course. We were discussing that we need to have a redshift to do all the, for example, SED fitting, but maybe better to have a probability of the redshift to use for different tasks we have. We also discussed if the redshift and physical properties should be delivered from the same code, from the same group, or separately. And also Galaxy is a more complicated object, let's say, than just a Galaxy, because of course we have some AGNs, and sometimes we have to classify between stars and galaxies and etc. So we want to also proceed with some quality flags, which can be also given to the community, and of course challenges. So this is also important, and I think that this is the main thing we want to do now. So during the meeting in Paris, we also presented some results from our group based on the PhotoZ and SED fitting. They are not all of the works which were done inside the group, but those are where we were really discussing during the meeting. So, for example, here you have the one of the project which checks the differences between the backpies and prospector, which the project lead is Vivir Kumar and Yogesh Vadadekar. I'm sorry, I'm very bad with names and surnames. So here, what you can see, they use the data from ECDFS. So you have they use the music deep optical to near infrared coverage for 16,000 galaxies, and for them they run SED codes with backpies and prospector. And then what they did in the next step, they removed all the infrared infrared data. So then just from nine bands, they moved to. Maybe I should do that. So here we have the results of the main sequence. So we have the stellar mass here and the star formation rate on the y-axis. And this is the result from the 9 points, photometric points. And this is the same run with the same parameters using only 6 bands, similar to LSST. So the main result is that using only 6 bands, we increase the scatter on the star formation rate from 0.4 to almost 1 day. So this is something we have to be aware using LSST data only without any auxiliary data. We also discussed the Photo Z challenge. It's also in-kind contribution with the project leads for. Somebody can help me with the surname? Ksiek and Lin. I'm sorry, the first one is very difficult. So this is the project with using the software, the Python software, rewrite one from the DEMP. And so they check how they can improve the possibility of obtaining more realistic photosys. So here on this plot, you have the redshift from the survey, like the grand true redshift versus the one from the photosy. And this is the training sample. So the sample it was used for the machine learning part. And this is the result. So you see that it's not that bad. So we are very close to find a good photosy pipeline. However, we have some outliers, but this is the same with the training sample. So of course, finding a training sample for the whole LSST is going to be a huge huge problem. But a lot of work on the photosy are now ongoing inside the Galaxy group. So if you have some ideas and you want to help us, please join us. Simona said it's not difficult to join our group, and we are very friendly. So if you want to join, we are really encourage you to play with us with the data. Also, this is the part which I'm not very photosy person. I'm more the CD person. So we also did a lot of work about SED fitting. Here, this is the result from the work of Gabriele Riccio. So we are trying to find if we have any problems with the estimation of the star formation rate for galaxy like LSST like galaxies. And we have found that using only LSST like data, we can really overestimate a lot the star formation rate, especially for the low redshift. When the bands from the LSST do not really cover not the mid infrared, not the far infrared bands. And we started to think from this work. It was work which was published in 2021. If we can find any proxy for the SED fitting codes for the dust attenuation. So this is the work we are really working on now, and it's not very easy. So then some years later, we try to find if we can use only observable data from LSST, so only colors and surface brightness, to find a proxy for the attenuation. And here you can see that those are results from the SDSS data, so 50,000 galaxies. And the run based on the run from the catalog from Salim, when he had a lot of auxiliary data and from far ultraviolet to infrared. And this is what we obtain if we use even the same parameters for the SED fitting, the same tool, but only for the LSST data. So you can see that this overestimation, it was found by Riccio, is still here. still in place. So then when we use this additional attenuation prior for the dust attenuation, we can really recover at least the low mass main sequence plane. No, it's not perfect yet, but we are closer and closer to that. So then there is a project led by me and Junais, and was also a part of both on the LSST and Euclid group. So we are trying to use some attenuation priors also from the simulation. So we are using Simba simulation and Power Day. Power Day. This is the simulation that really treats the dust, the evolution of the dust. So we were trying to do the same work. We are still not very good. We are still have some overestimation for the higher stellar masses, but we are still much better than without any priors. So we are working on the priors. Then probably Aaron will say more about this work. So here probably everybody heard about this work. So this is the data based on the ultra diffuse galaxy with the data from Euclid and Rubin. So Aaron did acidity fitting, common acidity fitting with all the data from Euclid and Rubin to check if our tools are ready for this kind of data on this very low surface brightness object, and also tried with the DESI spectra the fitting between photometry and the spectroscopy, and it looks that we are almost there. So we are having a lot of success in our group. And also we discussed during the meeting LEFAR. This is another tool for both for the SPEC-Z and for the SED fitting. So this is something new for LEFAR, that we also have the AGN fraction, like the AGN influence inside the code, so we can do both the host galaxy fitting and the AGNs. And we were checking how does it work. So both for using the LEFAR for the photo Z estimation and for the physical properties. I don't want to take all the time. I'm sorry. I was sure that I'm going to speak for 5 minutes, and I'm speaking, so I will try to make it a bit faster. So also we discussed a bit of LEFAR photo Z at a higher redshift between 3 and 7. So this is the work which was presented by Rebecca. So she is an expert in that, but you can see that we have high redshift galaxies for which we can use the already known tools like LEFAR to obtain physical parameters and SPEC-Z for those galaxies. So then we also discussed other possibilities for the redshift estimation from desk. So we discussed how this procedure is performed in the desk, and we try to learn more from this group, especially if we want to perform this challenge. We don't want to start from zero. We want to learn from others as well. So it was also a point of our discussion. So to conclude, so we discussed that, for example, when we want to do the main physical parameters, it's good to have information also about the active galactic nuclei in the galaxy. We discussed a lot about the SED fitting procedure for low surface brightness galaxies, because in general we don't have a large statistics for that, so we don't know if what we are doing is what we should do, or maybe we should think about our models. So this is something very important. We discussed about the challenges, the photo Z and the SED challenges, and of course we want to finish these challenges not only with giving you the documentation, but also to write the papers about those challenges. And we discussed that we should have like the smaller meetings dedicated to the specific group to make our work faster and also nicer, because it's always nicer to work with other people in general. And yes, so this is mostly all what I wanted to say about this part. Sorry for taking so much time. Okay, but you know, I think that the main conclusion is that as a group we are really very open, and we would like to, you know, even during meetings and the sessions here, we realize that a lot of people here are doing very good work, and you know, we can really join our forces to take our best from LSST. So this is all I wanted to say. If you have any questions, I will try to answer, or maybe we can have a discussion later, right? Thank you. Probably I should give it back to Aaron.
To Nandini first.
Now it's Nandini.
No, Aaron first. Okay. So please don't be shy, ask questions.
And also we have a Slack channel for today's session. So if you want to ask something on the Slack, I'm trying to check. You also I will give it. Thank you.
Any questions? And then
Oop. Reversed. Okay. Yeah, so I'm going to just to talk about low surface brightness results from early Rubin data. This is going to be very biased toward my group's work. I know there's other people have been doing work in this. It's very good. I just don't have any slides to show for it, so I'll just show you what we've been working on at San Jose State at UC Santa Cruz, and hopefully give you a preview of some of the capabilities of Rubin for this type of work. And you know, I kind of realized after we were in this room that these screens are not great for showing low surface brightness. So if you maybe everybody should turn around and look at those monitors.
do you want me to put the shade? Yeah, shade down.
Is there a way to do it?
Where is the technical?
How put the screen there?
On the other side.
We just need to pull it down, right?
Yeah.
No.
Yeah, I see. Can you put the screen down?
Oh, not the bottom.
Yeah, you know where?
This one goes
Yeah, it
down.
should be something like that.
No, you can't.
We can do it.
Lower it?
No, lower this.
Oh.
The window.
The window, yeah. The shade. Yeah. Oh, it's mine.
Oh, there it is.
Oh, we were looking for.
All right.
Thank you so much. Sorry. I was looking for the one.
Several students have led these projects, and they're in this room, so you can talk more to them about details if you're interested. Let me just say, first of all, like how people who work on LSB science know that the treatment of the sky is a very important factor. The question is, how is Rubin in this area? As you know, it's kind of mixed right now in the early days. It's not what it's optimized for. There's a giant nearby spiral galaxy, and that's what the Rubin DP1 image looks like in the sky. Classic donut hole, as everyone's familiar with. And in most general purpose telescopes, that's going to tend to be a problem. The good news is that, one piece of good news is if you stick with more distant galaxies, smaller things, less than 1 arc minute in size, it seems to be okay at the moment with DP1. DP2, I had a quick look, probably similar issues as we expected. The good news is that we have people, in-kind contributors from the UK, such as Aaron Watkins, who are working on improved sky subtraction, which hopefully we'll start seeing in DR1 and beyond. So, the ultra deep, ultra wide field, LSB stuff we're going to have to wait a couple years on, but hopefully we'll get there. One of the things we'll be interested to see is what is the true depth going to be of the LSSC for low surface brightness science. There's been various estimates by people, somebody in this room as well, and it's pretty broad range of predictions of how deep we'll really be able to go. And the magic number says about 30 is where things, substructure, for example, around galaxies really start showing up. So we'll see if we hit 30 magnitudes per square arc second. Also, just to mention, there's a lot of synergies with, you know, a lot of different large-scale sky surveys happening now, and Euclid being one of them that's overlapping with Rubin LSST, and then there are different synergies you can use with those different ways of getting at low surface brightness science, which I'll show. We don't know yet, you know, how deep Rubin's going to be compared to Euclid, for example. Of course, it provides the U bands, which is good for you know, stellar populations. The optical in general will be good for stellar populations, which Euclid doesn't have. And then the Euclid and Rubin provide the near infrared, which is also helpful for stellar populations and for selecting galaxies and selecting stars and globular clusters. And the space-based, of course, has the fine details for associated star clusters. So here's the first look at a ultra-diffuse galaxy, a special type of low surface brightness dwarf galaxy. This is what it looks like in the Legacy Decal survey. It's literally called a smudge because it looks like a smudge, and a lot more fine detail in the DP1 imaging, the Euclid, extended Chandra deep field south, equivalent to about 13 years of LSST depth. So that's kind of a preview of what we might see in the future after the full survey. This smudgy thing is resolved and it's got some fine structure. We could actually see globular clusters in it, even though it's about 50, 60 megaparsecs away, we estimate. And that's what it looks like in Euclid. And you can kind of start seeing some differences. Of course, you see the globular clusters and much more obvious point sources, but perhaps not the same low surface brightness depth that full LSST will have. And we just showing us that LSST will be a low surface brightness dwarf UDG discovery machine. And also we're interested in globular clusters with that. We started doing some science with this. Imang is in the back there, led the work on the SED fitting for this well, we have the luxury, this is a deep field, there's a lot of nice data from ultraviolet to the near infrared, and able to back out quite some detailed stellar population properties for a very faint object. Star formation history, get some idea of the quenching time, metallicity, mean age, dust content, all these different things. You can break with the degeneracies, you can break with the multi-wavelength imaging. Possible for this particular UDG, for those who know the field, there's like different models for them. This might be one formed by internal feedback causing a bursty star formation, which blew it up. Also, Sierra Blackhurst is a student here to presented earlier. She's following up with some work on morphologies of these objects and with a traditional CAS parameters. And so we're working on that, trying to, with a deeper imaging, again, you can go beyond just as a smudgy thing you can barely see. Now you get much more detailed characteristics such as classical morphology indicators. Well, okay, how about now DP2? I've just barely started looking at this. I don't know how much other people have looked yet. This is the same object in DP2. Didn't expect it to look quite the same because that particular field is only covered at 1 year LSST depth. So just a preview. We're not going to be able to say too much in that area. There are some other areas that are deeper I'll get to later. One question, I know there's been constant questions about Virgo and people looking forward to Virgo. So I started looking at that because it's obviously spectacular. We saw it in the publicity images, but also it's spectacular because it's deep. It's about 5 years equivalent LSST depth, and the sky subtraction, everything looked pretty beautiful in that. But we were kind of previewed that the sky subtraction in DP2 would not quite be the same, partly because it was very manual, maybe not calibrated sky subtraction that was done. So here's an example of an ultra diffuse galaxy in the actual DP2 data. I haven't done anything quantitative with this yet. You can see that you can detect it with a high signal to noise. This is about 26 magnitudes per square arc second. So that's pretty good. I mean, I would expect, it looks like we're going to get at least a 27, maybe 28. I don't know. It doesn't look as good as it looked in the first look imaging. Again, we expected that. So I'll be looking forward to getting more quantitative analysis of this region. This is an example of like what would be pushing the limits. This was a known UDG, and the NGVS survey of Virgo with the CFHT megacam. It's about 28 magnitudes per arcsecond. And this was from the first look data reduction. So it looked like it was very clearly detected. I haven't looked at this yet in DP2. I expect it's not going to be quite like that. You know, again, hopefully as we get into the full DR1 sky subtraction and getting deeper images of the whole sky, we'll start getting those great depths. And again, I don't know what happened with DP2 on this one. Also, just to mention another student here, Bill Dramati, has been looking for surveying all the dwarfs in this Virgo region, first look, and has found lots of new ones. And this is one of the new ones he found. And you can see that's the first look on the left and the DP2 on the right. So again, not quite as deep as in the publicity images. But stay tuned. So now turning to a different subject, LSV is halo substructures. Again, very important topic for galaxy formation. This is Gina Johnson, who led this work. She's here. And this is in DP1, again, focusing on distant galaxies so we can get good sky subtraction over that very limited region. And this is the, Gina spotted lots of different substructures, but this is the one we just thought was the most dramatic to really focus on for the first paper. It's very long stellar stream. It's about 130 kiloparsecs long, analog to the giant southern stream in M31 around a massive galaxy about redshift of 0.1. So that's reaching a depth of almost 29 magnitudes per square arcsecond. And so again, we're looking forward to seeing what the full LSST depth is like. Yeah, lots of substructures. And again, we heard earlier that there's also a need to automate this, and there's work underway to automate, you know, not just eyeballing everything, but really to automate detection of low surface brightness across the sky. This is another one in Virgo, which we published again from the first look imaging, a very spectacular stream, which was interesting because this is a Messier galaxy. Obviously, we've known about this galaxy for centuries. It was thought to be a prototype of actually an AGN that is triggered without a trigger, external trigger. So I thought it'd be a case for like why you don't need an external trigger to have an AGN. In fact, it has an external trigger potentially, and this unknown giant stream there that was easily detected in the Rubin imaging. And you know, again, the idea is that all the galaxies, as we start going to 30 magnitudes per square arcsecond, this galaxy and others should be in standard cosmology, just surrounded by a wealth of accretion features, as we already know in the Milky Way. This is not low surface brightness so much, just to kind of whet your appetite for DP2. You know, these are some examples of some nearby galaxies. I know, sorry for high redshift galaxies people here, but I'm showing all low redshift stuff. And there's some interesting nearby ones, and in some of the deeper imaging, you can possibly see some actual, it looks like a shell feature or some disturbance there and the extended stellar envelope there. So now this is, you know, with a science grade sky subtraction, and these are again a little bit farther away, so you can hopefully get some good sky subtraction on these. And that's all I had to present. Thank you.
Thank you. Any question for Aaron? Oh, quiet. Okay.
Yeah, I have a sort of a composite question for all three of you so far, right? Because of the AI use. CNN is obviously very important to the stuff you presented. But like for Katya and Aaron, your work and the reliance on what AI will be used going forward for FCPs or for low surface brightness features. What do you think?
Okay, so for Photo Z, I'm not an expert in Photo Z, so I don't want to really
SED.
For the SED, I'm not really sure if we should rely on the AI. It's my personal opinion. It's not the opinion of the Galaxy group, right?
That's the interesting question that I have, right? Because I personally also am a little worried about it, but I'm an old fart from a long time ago, right? And is the collaboration feeling like we want to head toward using something more AI-ish?
So there are different groups, as Simona can say, there are different groups which, for example, there is a group which wants to use the machine learning algorithms for the CPC. My problem is that, for example, for the low surface brightness galaxies, we don't have sufficient training samples. And if you have a training sample, it's also, some kind of bias because we are observing only the bluest and the more massive objects, right? So, but this is my concern, but I am not an expert in machine learning, so probably there is somehow a possibility to use machine learning for that, but I have my
Concern.
concerns about it, right?
Well, AI covers a lot of different things. I mean, we do certain things with machine learning where, the emphasis is on very careful testing and validation of things to make sure that the results make sense. It's very controlled. It's not, the type of thing that's generative AI that's hallucinating things. It's, for example, a convolutional neural network. You can test that very carefully, make sure that it's not giving you nonsense.
Right. So the testing part is a really huge part of all.
Mm-hmm.
Yeah.
And so the testing, the confirmation, I myself, the work that I do, I'm very concerned about false negatives. Right, false positives I can deal with, but false negatives are really, really bad. So that kind of thing is the sort of testing that's moving forward well in your opinion.
Yeah, well, and that's also depends on your science. So if you're, you can optimize for false, against false negatives or against false positives. Depends on what you want. And so you can really set up your training and metrics you're using everything so that you're getting that which trying to eliminate your false negatives, for example.
If I may just add to that, I think the false negatives can, of course, never goes down to zero.
Right.
But having an ensemble of different kinds of models that have different areas of failure in the parameter space sort of mitigates this. We are not quite there yet, but definitely I think using this ensemble method and using sort of relaxed confidences on each of them and then combining that information is getting us ahead.
It's like the olden days where we would run Galaxy SEV through both Fair and Sigel at the same time and decide which one is right.
Yes. But I think that, for example, machine learning is amazing for the detection, for example, for the structure detection of the images, because you cannot do it in a different way. Okay, you can do you can check the images by yourself, but sometimes it's in the so deep in the background that it's even for.
But even the human checking has a failure rate, which is why we use 20 different classifiers in the same thing. Right? Yeah. So that, but AI.
Yeah.
Thanks.
More like a comment. I actually work on something called DeepDiff, and it's basically a model that does the redshift part and it does the detection and everything. But for DP1 and DP2, the biggest problem is that we don't have sufficient ground truth. So you guys were talking with the test. Test is the important part. So how I was doing it, so I just put out my first paper on, but we usually look at other telescopes, like Hubble Space Telescope has a decent overlap with the ECD SS field for DP1, and that's what I basically use to compare my results. Yeah, but it is possible to use AI stuff for redshift estimation. So my group basically does both. They do star galaxy classification detection, and you can also find the redshifts of these things. So yeah, my next target is DP2 basically. I'll just figure out which telescopes are overlapping with it, and kind of Hubble Space Telescope is kind of the ground truth. So there's techniques where I'm mediating the training part, because you have to kind of create a training sample and you don't have ground truth. So what do you train on? So I'm using Scarlet for now, but there's AI algorithms that are self-supervised models where you don't need to rely on these ground truths. You can just feed in the images with only 10 or 15% overlap, 10 or 15% ground truth, you can do the rest of it.
Oh, that's a little scary.
Yeah.
Yeah, I mean, that's my main project, but
Okay.
I won't graduate if I don't do it.
Yeah, one more comment.
Yeah, I think everyone's making a lot of really good points, especially with the fact that whatever CNNs we do work on are going to have they're going to be just as good, but also just as bad as us. So, I think that it's probably worth exploring, like trying to have like kind of like a two-pronged approach where like you are using machine learning and you have like some human component that is driven to like find those anomalous detections, the things that like we aren't entirely sure that a CNN is going to capture or any other kind of machine learning model. There's also like newer networks out there that are like the goal is to try to find these like anomalous things so that you can like shrink all of your like failure modes. But I think that like I wouldn't rule out using AI, but I think that it's important to approach AI more as like the tool and not the solution.
And then I don't know if on this side of the room we have more comments. People using the AI. Okay. I would like to add something on that for standard galaxies. So for the most massive galaxies, it's actually extremely useful because you will have a lot of galaxies in SSD. So it's completely impossible to morphologically classify and derive redshift, propagation rate, etc. So and stellar mass, for example. So what you do with SSD fitting is to derive these galaxy properties, and you can do it for small samples. And for the small samples, we won't have the data to train the network. So the network will have difficulties to learn what the superbrightness galaxies will be. While for normal galaxies, we now have millions of galaxy samples in which we can train and verify the network. And CNN are extremely efficient to derive photometric redshift, stellar masses, and transformation rate, and the galaxy structural properties, such as size, etc. We're also using the lot transformers because if you go with the large transformers, they are slow, but if you go with other kind of small transformers, it really works well. And we're testing that, and we're testing the also fundamental models. So how this think, right? So you take models that are trained on a lot of data, multi-wave photometry, plus spectroscopy, and then you kind of use them to predict what you will find in small sample. And there are three who are really adapted to astrophysics. I think it's Ion, Astro Ion,
Ion,
yeah, Ion and Clip. Astroclip, and another one. So that they train on a large amount of data, and then you retrain them on a small amount, on a small sample to derive the galaxy properties. If you don't have a large training sample and you observe with another survey, for example, if you use as DSS to train, so that you learn to the other types and stuff like that, and then you have another sample, for example, from the DC2 simulations for LSST. If you can have a 10% of objects from DC2, actually the network can learn, when he has the basic learning from something large and then he learns a bit on a small sample, then you can use it on the small sample to classify it for regression to calculate the So there is called an hybrid approach, in which you use things from this. But there is a lot of study on how to transfer, for example, the weights that contain from network training in some survey to another survey, and how we do that. And we are learning more and more how to do it in a very efficient way. So I think the use of artificial intelligence in the Rubin galaxies will be expensive.
Okay.
Just that satisfaction.
Great.
Other questions on this? Or how do you function in general? Publication policy, do you agree with our lightweight approach?
Yes, we are.
Yes, I know that you are. And somebody wants an heavier process to publish. Yeah.
No, to make it easy.
Right.
Is Nandini still giving
Yes,
talk?
and Nandini, yes.
Yeah.
And we have another last talk. I think about this question for us in the part. Now Nandini is the last topic.
We have 3 5, I promise.
Yeah, but they are very interesting slides. So there are only 3 slides. They are very interesting 3 slides.
Hi, good afternoon. I am Nandini Hazra, and I'm a postdoc at the National Center for Nuclear Research, NCBJ, in Warsaw. And I will be talking to you a little bit in 3 slides about the DP2 readiness within the Galaxy Science collaboration. But I am going to speak to it through the lens of the people that I'm working with at the NCBJ and the people that we are collaborating with. I will speak by voice without any slides about the other people working on this, but this is by no means an exhaustive list. So please take everything with a pinch of salt. Right. So we have been working on a bunch of different topics using DP1 data and trying to get ready for DP2 data. In particular, what we started out with was to implement transfer learning models and take the weights that were generated by training on a large desk sample and then try and implement it within the RSP, which is something that we have done. We've used it to infer on DP1 data. We have candidates. We have recovered all the desk galaxies that overlap with the DP1 footprint inside the ECDFS. This is something that we have extensively tested and is working right now on the RSP in a very lightweight fashion. Secondly, on top of this, we are trying to sort of work around the biases of using this kind of transfer learning model. We are trying to detect and identify low surface brightness galaxies within the DP1 footprint at the catalog level. This is a significant challenge due to shredding at the low surface brightness end. Objects get broken up into pieces that don't really make sense, don't really fit together. We are trying and stitch that back together, and that is something that is in the pipeline. It's coming for DP2, so keep an eye out. If you don't like what we are doing, come and chat with us. Send us feedback. We love that. What we are also doing is we are trying to characterize the physical properties of the LSBs identified in this way. So we are trying to understand the holistic pictures of all of the LSBs that we see inside Rubin, what's missing, what's going wrong, what's going right, and so on. This is work that is being done by Saptarshi Pal, who's our student. He is preparing a paper on the DP1 sample that we have obtained, and hopefully we will be able to extend that to DP2 in the next few months, so keep an eye out for that as well. We are going LSB hunting. If you were there for my talk yesterday, you might have seen my memes. I only do 1 meme per conference, so sorry I don't have a new one. At the bottom left is an image of the ECDFS and the initial search that we did within the central region of this footprint, which was extremely deep, extremely homogeneous, had GNR band coverage, which we really like for this kind of study. On the top right is one of Saptarshi's low surface brightness galaxies, also in the ECDFS. So if you see this picture again, remember Saptarshi. On the bottom is the overlap between, in this footprint, is the overlap between known low surface brightness galaxies and the DP2 footprint. We're trying to see what the wavelength, what the filter coverage is like in that region, and see what we can obtain from the data that we have in eDP2. This work is also supported by Kasia and Agnieszka, who could not be here because she's in the IDAC session, which is a great segue to my next slide. We are also partnering with the Polish IDAC to test our science cases and potentially become open to global users. The timeline for that is TBD. the person working on this extensively is Krzysztof Nawrocki, and if you have questions about the Polish IDAC, please get in touch with Agnieszka, who's at this conference, or Krzysztof. So one of the test cases that we have been trying to run is to try and perform force photometry on Rubin DP1 data, using it as an auxiliary data to GWST. And we've been doing this with varying levels of success, and we're trying to see how we can make this work. The Polish IDAC also runs the RSP, so it's going to be a smaller adjustment for users worldwide who already use the RSP. So this is great. Additionally, what I mentioned, the project about search and identification of LSB galaxies and DP1 and DP2 using statistical methods as well as transfer learning. This is something that we will also attempt to test on the Polish IDAC. People who run the Polish IDAC are on holiday, so we're waiting for them to come back and we can get going. Krzysztof has also been working on developing new machine learning algorithms for detecting LSB features in images, independent of the use of standard pipeline catalogs. So the standard pipeline catalogs are a significant challenge because most of our transfer learning right now does not work directly at the image level. Primarily, it relies heavily on a pre-selection from the catalog, so you are only as good as your initial catalog. And this is a significant challenge. We want to eliminate this, so we want to go to the image level directly and try and make all our inference there. So this is something that Krzysztof has been working on at the Polish IDAC. And again, if you have questions about that, I will try to answer them. If I cannot, I will redirect you to Krzysztof. So please come and chat with me if you want about that. Finally, I've been talking about all these detection problems and how we can get more and more LSB galaxies, but what do we do once we have them? And what do we do once we have all of their physical properties? So one of the science cases for this, which has been tested already using galaxies that were obtained from transfer learning in DES and HSC, is this work on how to place these LSB galaxies within the large-scale structure and see if there are preferential differences between the properties of the LSBs themselves and how they appear in the large-scale structure and different environments. This is a slide from Agnieszka. And so what Agnieszka found, what Harish found in his data, and then later on was tested extensively by other people such as Junais, was that there is a separation between how the blue and red low surface galaxies are clustering in and how they are appearing in the closer to the center of the cluster and away from there. And if you have questions, please ask Agnieszka. This has been tested on the HSC data as well, and now is being tested on kids data by Unnikrishnan Suresh Kumar. So keep an eye out for the publication that will come out then. This is setting us up for testing all these similar studies using angular correlation functions and looking at galaxy environments and looking at the large scale structure through the lens of these LSBs, or rather looking at the LSBs through the lens of the large scale structure in DP1 and DP2 in a limited sample. But anyway, this will be pilot studies and will set us up for greater success when DR1 comes out. So we'll be prepared with our techniques, we'll know what the pitfalls are, and we will get there faster. That's the end of my 3 slides, as promised. If you have questions, I'll be happy to take them or redirect you to people who can answer them better. As Simona and Kasia also mentioned, there is significant work within the Galaxy Science collaboration, especially the morphology classification challenge, which will also have a detection component to it. Lisa Sazonova is the person who is, I believe, the contact person who is running the challenge. If you are interested in looking at LSB galaxies through the lens of mergers or just mergers themselves, Will Pearson and Aidan Cotter are working on that at the NCBJ as well. If you want to talk about how to coarsen Euclid data to make it look like LSST and test your algorithms there, Anirban Datta is the person to talk to. So whatever your questions, I'll be happy to try and find answers for you. Thanks.
Let's thank Nandini. Any questions? Yes, Jim.
Could you please tell me what transfer learning really is?
Right. So what transfer learning is at its core is basically using, so taking data from surveys. In this case, in this example, it was DES data. So the models, it was an ensemble of different kind of, they're called transformer models. And these were trained on data from DES. And then these trained models, these weights, were then taken and applied to the other data sets, in this case, HSC and kids data. The way this was done was by adapting the pixel scale and 0 points and sort of making them similar, like normalizing them to the same level, and then trying to infer what is happening in the HSC data and then later on in kids. So it turned out that it worked very well for this kind of identification and inference in HSC data. The transformer models found LSB galaxies that were not found before. And it also, this kind of domain adaptation allowed it to also search for galaxies that went slightly deeper than even its training sample. And this was validated very well. So it lost the objects that were in the halos of very massive bright galaxies, but it performed very well for objects that were more or less separated with clear borders. So this was transfer learning in this context. I think the general idea is to just train it on one data set and try and use it to infer things on another data set, similar but slightly different data set.
So is it transfer learning is just anything that uses transformers?
Yes, yes, that is, yes.
You
No.
can transfer
We're
learning
gonna
to
other-
CNN.
You can do it with CNN too?
Yeah.
We use an ensemble which also includes CNN.
Okay.
But yes.
It just means what Nandini just said.
Yeah.
So you train the network, whatever network, on one sample, and then you use the training on another sample.
Fair enough. Okay. Thank you.
And it's not easy. I mean,
A known caveat is that if you try to do this between ground and space-based data, you run into problems. If you translate between different ground-based data sets, you sort of can get there. Yeah. Sorry, Aaron, you were saying something. I interrupted you.
Oh, I kind of think of it even more generally. Like imagine you've got your UGRI filters in one telescope.
Yeah.
You want to use the same filters as another telescope. You know they're not exactly the same band pattern. You can't just do exactly the same analysis. You have to do a little bit of recalibration. So you're kind of using the same analysis infrastructure, but you just adapt it slightly to your systems.
Yeah. Like the old-fashioned color terms or something.
Yeah.
Yes, similar.
In an AI.
Yeah. On an image
Machine
scale.
learning.
Yeah.
Okay. Thank you. That's great.
And there is also nifty things you can do with binning the image down, so things show up more clearly. Yeah,
Nice.
we can chat about that
No,
later on as well.
no, this is very helpful.
Thank you very much, Nandini.
Thank
Other questions?
Any questions, comments, feedback, concerns?
Okay, very good. Let's thank again Nandini.
Thank you.
We have 5 minutes if you want to. Now we have 5 minutes for comments, feedback on the SC. And if you don't have them right now, please reach out to Sugata and myself. And we are finalizing the publication policy and the governance documents for the LSSC at Europe 8. And then we are ready to work with the data. Thank you for coming. Bye. Bye-bye.
Thank you so much.